All right, so just first thing, let me just talk about the numbers you're seeing at the top. The first number is your raw score. That's what you would have gotten if I didn't curve the exam. So I decided to curve the exam because there wasn't even, let's think, there may have been like 2 or 3 90s, but low 90s. So I felt like maybe the exam was more difficult. I'm not sure, but the grades were fairly low. So I decided to curve them. And like if you were to look at your raw score and then your curve grade, but then went to somebody else's, you're not going to see the same amount. And that's because I did this strange thing where I did this square root curve, which kind of like helps the lower grades a little bit better than the top grades. But then I also did this linear distribution curve and then like took the average. I did this whole thing to try to give sort of the maximum amount that I could give you, just because I don't want to see your grades for the semester tank. So then the grade after the arrow is the curve grade, and then I either added points or subtracted points based upon the 3 homework assignments. So most of you probably see a +6 there. And then the circled grade is your grade. If you want to come up, I'll give you yours. So the grade in the circle is what you should see on the D2L site. So I'm just going to quickly go over the exam. I would also suggest, just to make sure that I input the right grade into the D2L system. And again, I don't care. If I made a mistake, please tell me. I'll update it. It's not a problem at all. Okay, so believe it or not, and I was a little shocked, in this number 1, all I wanted you to do was determine the domain of those equations. I would say probably there's 20-some people in the class. Probably 15 of you tried to solve these equations. All I wanted was the domain, right? So you just have to worry about, and the domain's going to come up again. So just, we're defining domain as the set of numbers that when you plug those numbers in for x, you get real solutions, right? So you want to exclude anything that gives you either an undefined solution or a complex number. So in this first one, all you had to worry about was the 6x plus 4 term in the square root. That has to be greater than or equal to 0. Otherwise, it'll be complex, which means x has to be, once you solve down, x has to be greater than or equal to -2/3. So I wanted it in words and interval notation, so all reals where x is greater than or equal to -2/3, or then here's the interval notation with the bracket, because we're greater than or equal to, and then it goes to positive infinity. The second one, all you have to worry about is the denominator, okay, x minus 4. We can't have, there's no complex numbers here, but we have a possibility of being undefined when x is 4. So x can't equal 4. So the domain is just all reals except x equals 4. And then again, here it is in interval notation. So that kind of sucked because I thought, I don't know why people decided to solve those, but I was just looking for the domain in that question. All right, so the number 2. These were questions from section 1.5. This first one was a rational expression, right? So all I did, you'll see here, is I took all the denominators, right? So 6 times x plus 1, and I multiplied each term, and that multiplication goes into the numerator, and you'll see that things cancel out, and then you'll get down to a simple quadratic equation that's factorable, and you'll get 2 solutions, -3 and 2. Now the second one, so I would say a lot of people did that first one correctly. This second one gave people a lot of trouble. So what you do is you isolate the square root term and then square both sides. And then when you do that, you end up getting a simple quadratic that's easily factorable. You just take out an x, and then you get 2 solutions, x equals 0 and x equals 10. But these are the problems where, since we're squaring the terms in the equation, we're actually increasing the degree of the equation. So some of those answers might be, we call them extraneous, like they're just not correct. So you have to check both answers. And when you go ahead, if you check 10, it works out. But if you check 0, you get an equation that looks like 4 does not equal 0. So x equals 0 is not a solution. So there were those 2 problems. Number 3, everyone did this mostly well. Just identify which ones were identities. First one's not an identity because it only has one solution. An identity, remember, has a domain of all possible x values. So you could plug any x value into this equation and get a result that's true. So the second one is an identity. Not too many problems here with 4. Again, I had these square root of negative numbers in here to make sure you would convert them into complex. So like the square root of negative 25 is just 5i. And then you have to go through here, and then every time you see an I squared, change it to a -1. And then standard form, remember, is the real part of the complex answer plus or minus the imaginary part. So 20 plus 8i would be the solution for that in standard form. This middle one ended up being just a real number, 25. And then the one on the right, again, some of the same people who made this mistake from quiz 1. I'm not asking you to multiply anything here. This is just, you're subtracting a quantity, 1 plus 2i, so you're just distributing the negative sign. And then that just becomes a very simple, 6 minus 1 is 5, and then I minus 2i is negative I. So some people overthought that and thought you had to multiply. That was the first page. Number 5, I had to put something on here from section 1.2. So we did, basically this exact same problem. So like if you were studying the types of problems from section 1.2, I was hoping, I basically just put one on there with different numbers, but, a lot of people screwed it up, but the final answers were 15 feet and 30 feet. Essentially, here's the equation for perimeter, right? 2 times the length plus 2 times the width for a rectangle equals, and they give us the perimeter of 90. And we know that the width's in terms of the length, and then all you then have is an equation with one variable, and you solve it. And then plug that back into the width equation. All right, 6. 6 was, here's a bunch of quadratic equations. Use any method that you know to solve it. So some of them, one method was easier than the other. So the first one was just factorable. You could have used the quadratic if you wanted to. It just would have had big numbers because you have an 84 in there or 25. But if you just knew you could factor 84 into 21 and 4, that was a simple problem. Now the second one, you could have went quadratic right away, but you're looking at bigger numbers, 6, 14, and 4. If you saw that you had a GCF of 2, you could take that 2 out and then only deal with this easier equation, 3x squared minus 2x minus 7, and that's not factorable. So I just went through the quadratic formula, and you would end up with this 1 plus or minus square root of 22 over 3. And then I was hoping for this third one here. I had this exact problem, different numbers on the last quiz 4. And I even structured it so it looked like you could just do the square root method by putting the 81 on the right-hand side, taking the square root of both sides, which gives you a plus or minus 9i on the right, and then the solution's pretty simple. So I was hoping people saw that. But I had a bunch of folks foiling out the x plus 5 and then trying to do the quadratic formula, and it just got messy. 7 was a lot of issues with 7. Write these quotients in standard form. So we're just rationalizing the denominator. So what we had to do here, I just took the denominator 3i and multiplied by 3i over 3i, and that gets rid of the i in the denominator, and you end up getting negative 2i over 3. And then this one over here, the complex conjugate of 4 plus I is 4 minus I, so we do that multiplication, and things actually end up canceling out. Now you would get 17 plus 17i over 17, so all those 17s cancel out to be 1s, and then the final solution is nice and tidy, just a 1 plus I. And then 8 was, again, wanted to make sure you could do this quadratic formula because that comes up a lot. Very rarely do you come up with an equation in some future class and you can end up factoring it. It's very, very rarely happens. So I wanted to make sure you could do this. And I wanted to give you a quadratic that had a quadratic formula problem that had a complex solution. So when you go through everything here, you would end up with 1 plus or minus 5i over 2. Now, one thing I want to point out here, and I'm going to I hope you can see my mouse, right? When you do the b squared underneath the radical, and b is negative, right? You're doing negative 2 in parentheses squared, which gives you a positive 4. Probably half of you left that as a -4, which kind of screwed up the rest of the problem. So just know if A, B, or C are negative, you have to plug them in there. But if you're going to square one of those terms, you're going to be getting rid of that negative sign. All right, and then 9, here we have our compound inequalities, right? So I gave you an OR. So an OR is basically you take the solution from each inequality and just, union them or add them together, right? So here are the two number line solutions for the two inequalities. So then the final solution in number line form has just both of those things. So the bracket going down to -infinity and then a parenthesis up to +infinity. And then here's the interval notation. Now for the and is intersection. So you only want the common solution between the two inequalities. So you solve the inequalities, you get x is greater than or equal to 1, x is less than 4. So here are the graphs. So essentially you want to the intersection is where you have the bracket on the 1 and then the parenthesis on the 4, and you just shade between, and then the interval is the bracket 1, 4, parenthesis. Okay. So I didn't really try to do too much difficult compound inequalities there. So a lot of people did okay. I noticed people were using circles and then solid circles, and you must have learned it that way, and that's fine. It's just, I'm trying to show you a way in class, and I think it's the simplest way. But I don't care if you want to use a different way. It's just make sure that I can understand the flow of what you're trying to show me, right? Because if you remember in class, this is how I did these problems. You solve the inequality, write out the number lines on top of each other, and then the third number line is your solution, and then you have your interval notation. Some people only gave me one number line, which is the solution. But if that was wrong, I had to take more points off because I didn't see the intermediary steps before that. So just keep that in mind. The more work, that's, the better. Now this one, a lot of people had problems with this one. I had a lot of people leave this blank. So it's a quadratic inequality, and I asked you to use the test point method. So what you do is you put everything on one side of the equation. This was a factorable quadratic, and you would get two values, 1/3 and -2. So I put those on a number line. And what our goal was to determine the three intervals on the number line. There were only three, from -infinity to -2, then between -2 and 1/3, and then 1/3 to +infinity. Pick test points. I chose -3, 0, and 1. So I tried to make it so that you had easy test points. You figure out the signs of basically everything to the left of the inequality symbol, and then multiply those together to get a result. Now, how do you know which part of the number line is the actual solution? Well, I put it down here, greater than 0, right? That's what this says here. Greater than 0, which means any place you see positive signs is where the solution is. So it's just the union between -infinity to -2, and then 1/3 to +infinity. Okay. And then no one really got the bonuses. The first one, if you gave me some sort of effort, I might have given you a point or two. But yeah, that's there. Don't worry really about this one, just to see if anyone caught it. Since we were saying x was equal to 1, this term x minus 1 is really 1 minus 1 or 0, so you can't divide by 0. So essentially that was the flaw in the argument here. Okay? So does anyone have any questions about the exam? Again, what I also would make sure is next to each problem, I marked how many points you earned, right? I would add all of those up and make sure it matches to that first number you see on the front page, because I could make a mistake adding them together. So just make sure that's correct. And again, if you don't feel like asking me a question now, feel free to send me an email and I'll certainly answer any questions. So I had given you section 1.7 homework. There might have been some confusion because I don't think I may have said something wrong in lessons, but I was not planning on collecting that. So there's not a Dropbox for it. And in fact, I'm going to move on to chapter 2 today. We actually started a little bit of it before the day before we had our exam. So I'm not going to be quizzing you on 1.7, nor will you see 1.7 on the exam. All right, that absolute value stuff, it doesn't come up so much. So we'll just sort of say, well, we covered it. We're just not going to have a quiz or exam on it. So the next exam and quizzes will be on Chapter 2 material. So that's where I want to start now. All right, so let me... So looking over the Section 2.1 notes, this is all we talked about so far. Hopefully everyone can see that. Yeah, everyone should be able to. I just, and this is something that is just a review. We reviewed the coordinate plane, the Cartesian plane. You have two axes that are perpendicular to one another. Where they intersect is, we call that the origin. The horizontal, we denote the x-axis, so there's a positive side, there's a negative side, and then the y-axis, the vertical axis, as you go up, you're positive, as you go down, you're negative. All right, and then we were able to plot coordinates. So I gave you a coordinate A, and we said it's 3, -2. So the 3 is the x-coordinate, the -2 is the y-coordinate, and you'll see I plotted A. So hopefully we could all do this. All right, I don't have to give you too many examples on how to plot coordinates. I think we're probably all okay doing that. Now, there's a couple things that we're going to do in this section that may come up later on. So I think that's why we're covering how to do some of these things. So the first thing we're going to figure out is, now that we know how to plot coordinates, it's going to be finding the distance between two coordinates. That's what we want to do. Finding the distance between two coordinates. All right, so I'm going to give you a set of axes. On any quiz or exam, I'll give you a nice set, but just for the notes, we'll just draw them out. So let's label 2 points. I'm going to label 2 points here. I'll just define them over here. Let's label a point A, 1, 3, and then a point 5, 1. So we're all going to be in the first quadrant. So 1, 2, 3. So here's A. All right. That's 1, 3. And then 5, 1, 2, 3, 4, 5. So there's B. So what we're interested in finding is the distance between these 2 points. So this is how we denote, this is a little bit of geometry, I guess, right? So if you have a line segment on a graph like this, we denote that line as AB with the line above it. All right, so we're trying to figure out what that is, the distance between A and B, the size of that line segment. All right, so what we want to do, and I'm going to get a different color here. What I want to do is, because we're working with a Cartesian coordinate system, right, that you could always make vertical lines and horizontal lines, right, that parallel the axes. So what I'm going to do is I'm going to make a vertical line that parallels the y-axis, and I'll just do that here. So I'm going to do this. So that red line is parallel to the y-axis. What I'm going to do at this point here, I'm going to make a horizontal line parallel to the x-axis. Okay. Now, since both of those lines, the red ones, are parallel to the y and x-axis, if the Cartesian coordinate system has a right angle here, we also have a right angle there. So you see that we're making a right triangle. All right. So we're going to have to, understand some things about a right triangle. So just, if I threw out a right triangle over here, okay, and by right triangle, we just mean one of the angles is 90 degrees. If we have two legs of a right triangle, let's say A and B, and the line that connects those two, we call that the hypotenuse, called C. we had a relationship between all of those. We called that the Pythagorean theorem. Anyone remember the relationship? What is it?
Isn't it a squared plus b squared equals c squared?
You got it. Okay? So for right triangles, that relationship is always true. So we just have to figure out how to get that relationship in this other graph. So if we just think about this for a second, right? This distance here, the horizontal red line I made, we could actually just do the change, like delta symbol, right? Everyone knows that's the change symbol. If we looked at the change in the x-coordinates, that would give us that distance. Because horizontal lines and vertical lines, their sizes are easy because we don't have to worry about going in 2 dimensions. They're just one-dimensional lines. They're easy. And then in the y direction, we have delta y. It's the change in the y coordinates between A and this point I made down here. Okay, so let's make an equation utilizing the Pythagorean theorem, okay, and the information we now have on our graph. So if I wanted to say, all right, AB, that line segment, right? That's like the hypotenuse. So if I square that, that should be equal to the change in x squared, right? That was the bottom horizontal line of this triangle plus delta y squared, right? So we just used the Pythagorean theorem. Okay. Now this will work for any line segment, not just specifically AB. So what I'll do is just to change this up, I'm going to say, I'm just going to call this D, right? This is a distance, right? D squared between 2 points is equal to the change in x squared plus the change in y squared. And now if I wanted to solve for D, I would take the square root of both sides. So I'm going to have a square root symbol over here. And I'm going to expand these delta x's and delta y's. So remember, delta x is just going to be, let's say, the second x coordinate minus the first x coordinate squared. And then we'll add to it the delta y definition, which would be y2 minus y1 squared. So that's it. We have what we call the distance formula. And this is used to find the distance between any 2 points on the Cartesian coordinate system. Okay. All right, so let's go ahead and do it. Now, as you practice these, you'll be able to throw this in here pretty easy. But what I'm going to do down here, I'm going to throw a different color in. So here's A, right? A we said was 1, 3. So let's call that x1 and y1. And then point B was 5, 1. Let's call that x2, y2. Because we have to know what those values are when we plug them into the distance formula. Okay, so this D, right, is really in this example AB bar. So that's what I'm going to put down here. So AB bar, which is really D, is going to be equal to the square root of, and we're going to plug these numbers in. So what we're going to do is going to take the difference between x2 and x1. So x2 is 5, x1 is 1, and we'll be squaring that. And then adding to it y2, which is 1, minus 3 squared. All right, so AB, what do we got? We have 5 minus 1, that's 4 squared, plus, now again, I want to make sure people do this correctly. When you do 1 minus 3, you're going to get a negative 2. But that negative 2 stays in parentheses. So that distance AB is going to be the square root of 16 plus 4, which is the square root of 20. Now, part of the reason we had you working with square roots before is like we do not want to leave the square root of 20. Can't that be broken down into the square root of 4 times the square root of 5, right? So then my final answer for the distance between those 2 points is 2 square root of 5. All right. Hopefully this is probably a review. I'm sure at some point in your lives you've done the distance formula. Now, one question that comes up a lot is, well, what if you labeled the A point x2 and y2 and then labeled the B point x1 and y1? Does it make a difference? Do you think it would make a difference? It wouldn't, right? So just as an aside, I'll just plug in real quickly. So if we switched it, so instead of 5 minus 1, we did 1 minus 5 squared plus 3 minus 1 squared. Do you see that you're going to get negative 4 squared plus 2 squared? And isn't that going to be the same thing as before? So it doesn't matter which one you label, right? As long as you're subtracting the x components and then subtracting the y components, you're good to go, okay? So yes, sir.
Will this be something we have to memorize, or
I'll give you the distance formula. Yeah, believe me, I'm not a big, you have to memorize things. So just like the quad formula, I'll give you this. Yep. You just have to know how to apply it. That's all. Okay, so why do we care? Well, we can use that distance formula to identify triangle types. Okay, so by the way, we already know we have right triangles, right? Okay, we know how to determine that, right? If a squared plus b squared equals c squared, we say it's a right triangle. What are some other types of triangles you remember from back in the day? Yeah, go ahead. So we have isosceles. And what is do you remember what isosceles? If I'm spelling that right, I think I might be. What does isosceles mean?
2 sides are the same.
Yep, 2 sides are equal. Now, you could have an isosceles right triangle, right? Yeah. But you could have a right triangle that's not isosceles. You can have an isosceles that's not a right triangle, but you could have those combination. Anyone else? I think there's 2 more that we really need to. So acute would be, what do you mean by acute? Okay, so that would be, there's acute angles? Like an acute angle is less than 90 degrees, right? Yeah. So that wouldn't be an actual type of triangle, I think. Well, at least the types that we're worried about, yeah.
Equilateral.
We have equilateral. Now that one is all sides are equal. And really, there's only one other one, yeah.
Scalene.
That's it, scalene. And that's all sides are different. So Liam, just from what you said, like for example, a scalene triangle can have an obtuse angle. Obtuse means an angle greater than 90, right? You could have, by definition, an equilateral triangle has all acute angles, right? So I think acute and obtuse have to deal with the angles inside of triangles, but these are the types we're working with, if that makes sense. So here's what we're going to do. And this is, and I don't know, I kind of like puzzles, and I don't know if this is a puzzle, but you're going to be given 3 points. So here's the first example. Okay? Here's 3 points. 3, 2 at P. Q is 6, 6. And R is -1, 5. Okay? So if you have any 3 points in the Cartesian plane, they can form a triangle, right? So let's sketch this guy out. And sketching it doesn't really give you a super good indication of what type of triangle it is, but we can use the distance formula to figure all this stuff out. All right, so I'm going to do R first, so it's -1, 5. Okay, so there's R. Q, let's see, Q is 6, 6. And then finally, P is 3, 2. Okay, so we can connect those 3 points. And here, I'm going to do some labeling here. The line between P and Q is PQ with a bar, right? The line between R and Q is RQ. And then the line between P and R is PR. Okay? We could calculate each of those distances. And then based on what comes out from that, we can determine what type of triangle this is. Which means we have to calculate all of these distances. Okay? So let's do that over here. So let's start with RQ. Now what might be really useful is to label x1s, y1s by your points up here. So R, let's call that x1, y1, and then Q is going to be x2, y2. And, I just arbitrarily picked those. So we're going to do the square root of, so x1 minus x2 is -1 minus 6 squared plus y1, 5 minus 6 squared. So what are we going to get here? We're going to get, so -1 minus 6 is -7 squared, which is 41. And then 5 minus 6 is -1 squared, which is 1. So it's 49 plus 1, so it's the square root of 50. And we can break that into the square root of 25 and square root of 2 and get 5 square root of 2. Okay. So at some point you'll be able to do those fast. So let's go through these other ones, because I'm confident you can do them, maybe just not this quickly. So let's look at PQ. So PQ, since I already have x2 and y2 labeled for that, I'm going to call this x1, y1. We'll do the square root of, all right, the x difference. So x2, 6 minus 3 squared plus 6 minus 2 squared. So we're going to have 3 squared plus 4 squared. So that's 9 plus 16. So is that the square root of 25? So that's just 5. It's very nice. That works. Did I get that right? Yep. And then finally, what's the only one we didn't do yet? We did RQ, PQ. We have to do PR. So for PR, I'll change these R1s to X2, Y2. Okay, so the X difference. So we'll just do -1 minus 3 squared plus 5 minus 2 squared. We get, so -1 minus 3 is -4 squared, so that's 16. 5 minus 3 is 3. 3 squared, 19. So it's, again, the square root of 25. So we get 5. Okay. Okay, so now we have the sides. So right away, what type of triangle is it at least right now? All right, so it's isosceles because we see two sides are the same. The last check, though, would be, all right, you can't have an equilateral triangle. That's right? Equilateral, they're all 60 degrees. Scalene, if you have an obtuse angle, like of 120, there's no way you can get a 90 in there. So the only type of triangle that could be a right triangle is isosceles. So we also have to check to see if that's true. So, again, when you look at a right triangle, the biggest length is the hypotenuse. So the hypotenuse in this case would have to be that 5 square root of 2. So if we wanted to check a squared plus b squared equals c squared, we would do 5 squared plus 5 squared equals, and then c being the biggest term would be 5 square root of 2 squared. So let's see what we get. We get 25 plus 25 is 50. And then let's see, if we square 5, we get 25. But then if we square root of 2, it's just a 2. So it's 25 times 2, and it's 50. So look at that. So if you plug the sides of your triangle into the Pythagorean theorem and you get the same result on both sides, you can also say it's a right triangle. So what we've created here is an isosceles right triangle. Ooh, I spelled triangle wrong. Okay? So we're going to use the distance formula or apply it to figure out different types of triangles. All right? Again, I'm giving you a process. You know, I feel like just because of the way I'm giving you the problems, like it might be beneficial to just follow the process I'm giving you. But again, you know, if you've known a different way to do this, go for it. But this is the process. All right, now the last thing in section 2.1? There's one more useful formula to calculate something, and it's called the midpoint formula. All right, so let's say I gave you 2 points. I'm going to say A is at 3, 2, and B is at -2, -4. All right. So I'm interested in figuring out the midpoint of that line. So I'll just, do a very simple sketch here. So A is 1, 2, 3, 1, 2. So here's A. B is -2, -4 here. So here's the line segment AB. We would like to know the midpoint. So we're trying to find another point. Let's call it C as the midpoint. All right. So here's the formula for that. All right. So again, you have to have two coordinates. So like, let's say A is x1 and y2, and B is x1 and y1, and then B is x2 and y2. Here is the formula. And again, you don't have to memorize it. The midpoint is, again, we're going to get a point here. You add the x coordinates and divide by 2, and then add the y coordinates and divide by 2. I mean, it's literally that simple. So if we wanted to do this midpoint, so we'll call it C. Let's add the x's together. So that's 3 plus a -2 over 2. And then the y coordinate is going to be 2 plus a -4 over 2. And then we'll just do some simplifying. So it's 3 minus 2, so it's 1/2. Comma 2 plus a -4, which is -2 over 2 is -1. So there's our midpoint, 1/2 -1. And again, I'm sketching it, so if you want, I'm kind of close to that, right? Like this would be where C is. It's the midpoint between those 2 points. I'm hoping going forward in chapter 2 that some of this stuff is a review, especially this section. This is pretty simple. So that ends section 2.1. So the homework, so this will be on page, it's 181. So here's the homework for section 2.1. This is pages 181, 182, and then there's one problem on 183. It's 15 to 21. Now those problems are determine the distance between points and then the midpoint, so they should be simple. And then the other ones are 35 to 41. They're determining types of triangles, so just like I did that example. And then I'd like you to do a word problem. Again, it won't be difficult, but I'd like you to do. I just want to see if there's anything else. I think this is a good one. 62. So you won't know the answer, but that's okay. We can go over that if there's a problem. And again, these are all odd at the beginning. So this is the homework assignment for 2.1. Now, I want to be clear. This is on Tuesday. This is the one I'd like you to submit to a Dropbox. It's very simple. It should be easy to get a plus 2 points for our last exam 3. Okay? So this is in the I'll even put it in the notes. In the Dropbox for Tuesday. What is it? The 20th? Perhaps? Put that in the Dropbox. Okay? 2-1. Very simple. All right. What's nice, I guess, about some of these sections in Chapter 2 is some of them are fairly small, right? There's very little information in each section. So we're going to move right along here with Section 2.2. And again, this section is also not very mathematically intensive. It's more graphical. All right, 2.2. Let's see what we can get done. Let's change the color. So section 2.2. And this is graphing equations. So we've been dealing with equations for quite a while now in Chapter 1. Now we want to start to be able to put them on a Cartesian coordinate plane. And I'll just give you a couple ways to determine how to graph some of these things, okay? A lot of times there's equations that you would need to use calculus for, but we're not going to use calculus. But what we're going to do is try to get the graphs to look as close to what they look like as possible. All right, so the first type would be to use a table to sketch a graph. So this is, I guess I can call this method 1. So this is using a table to graph. So first, let me give you the equation that I'd like to graph. We're going to try to graph y equals 1/2 x squared minus 4. Okay? Does anyone know what the general shape of that's going to look like? If something's an x squared. Yeah, it's a parabola. Okay? So we want to figure out the best way to graph this parabola. Now, again, to get this graph to be really good, a lot of times you have to use calculus, but we don't have that luxury in Math 106. Okay? So we're going to make a table of values. So what does that mean? Well, we want to be able to plot a bunch of coordinates to see the general shape of this graph. So what we want to do is we're going to make a table of x and y values. So the point is we're going to plug in x's and then see what the y coordinates would be. But you have to be, how can I say this? You have to think about what values you're going to choose for x, because this is very open-ended. Like, I'm probably not going to pick 13, right? Because if I do 13 squared, I'm going to get an odd number, and then I'm dividing by 2. So I'm going to get decimals. So I want to try to avoid all of that. So you see that when I square the x term, I'm then going to divide it by 2, and I want that to be a whole number. So what I'll do is, first off, what's one value that should always be in here, do you think? Right there. You want to put a 0. Okay, so I'm going to put that in the middle because I want some on the negative side, some on the positive side. Do I want to put 1 as a value? Because I'm going to get a half, right? And again, I'm just trying to avoid it. How about 2, though? I think 2 is going to be good. If I put a 2 and then a negative 2, I'll get whole numbers when I do that 2 squared divide by 2. I'm probably not going to do 3. Again, I'm going to avoid odd numbers, but I could do 4. Or negative 4 and 4. And then let's just do, I guess we'll do negative 6 and 6. All right. So what you want to do is you're going to be plugging these x values into the equation to get what the y value is. So we could do this rather quickly. So if I plugged a 0 in, you see that I'm going to get a negative 4, right? Because that first term here, if x is 0, just goes away. And then we just have to plug these in. So if I did a 2 I'd get 2 squared, which is 4 divided by 2 is 2. So 2 minus 4 is negative 2. 4 squared is 16. 16 divided by 2 is 8. 8 minus 4 is 4. And then 6 squared, 36 divided by 2 is 18 minus 4, and that's 14. Now, because I'm squaring the x coordinates, it doesn't matter if they're negative, right? Because those negative signs are going to go away. So for negative 2, I'm still going to get a negative 2y. For negative 4, I'm still going to get 4. And for negative 6, I'm still going to get 14. So now we have all these coordinates. And when you set up your x and y axes, you want to make sure that you go out to the most extreme x value and then the most extreme y value. So for x, the most extreme is 6. So 1, 2, 3, 4, 5, 6. And I have to go the same direction negatively. And then I have to get up to 14 in the y. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Again, that was kind of, I fit them in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There you go. So you set up your axes with the extreme values, and then you just plot them. Let me get a different color here just for, so it doesn't look so drab. Okay, so 0, negative 4. There's a point. Then negative 2, negative 2. So negative 2 is here. Positive 2, negative 2 is here. 4, 4. That's here. Negative 4, 4. So that's same spot. And then 6, 14. So I know they're at the extreme, so that's easy to point. Okay. So clearly that looks like a parabola, right? And now you just connect a line. Okay. Oh God, that was bad. Still not great at drawing on the surface. But there you go. You have a parabola. It's pointing up. By the way, this thing down here, this is the vertex of the parabola, right? It's the lowest point if our parabola is pointing upward. So really, you could be given any equation and use this table method to draw it. The only thing that sucks about it is it takes a while, right? It takes a while to go through all those things. So, there's probably better methods. And there's other things that we can do to help graph equations. All right, so that's using a table to graph. I think that's pretty self-explanatory. You just have to be smart about what x values to choose. All right, the second method, and this is a method that's going to help you determine specific locations on your graph, is we want to be able to calculate intercepts. Okay. Now, what do I mean by intercepts? I'll just point out in this graph. Right here at the vertex, that's where the graph intercepts or crosses the y-axis. Okay. Right here, which we didn't actually calculate, there are the x-intercepts. It's where the graph crosses the x-axis. So there's a way to find those values. Okay? Okay, so for x-intercepts, so we want to figure out where we're crossing the x-axis. What would be the y-coordinate of an x-axis intercept? Like, even look at the graph up here. Like right here, what's the y-coordinate? Isn't it 0? Right? So for y-intercepts, you set y equal to 0 and then solve for x. For y-intercepts, it's the opposite. For a y-intercept, your x value is 0. So you set x equal to 0 and solve for y. So intercepts always have one coordinate that's going to be 0 all the time. So as an example, you may be given something like this. Okay. We won't graph it, but let's make sure we can calculate the x and y intercepts. Okay, so let's do x-intercepts first. So we'll do x-intercepts. So we're going to set y equal to 0. So we have 0 equals 2x squared plus 3x minus 2. Oh, look. We're about to solve a quadratic equation, right? So were we spending all that time in Chapter 1 doing it? Well, here's an application of solving a quadratic equation. Now, luckily, this one's factorable. But again, you could use the quadratic formula, whatever. You're going to get, let's see, this has to be 2x and x. And then this is 1 and 2. And then this is positive, this is negative. Let's figure out these x values. So 2x minus 1 equals 0. X plus 2 equals 0. So 2x equals 1. X equals a half. And then x equals negative 2. So I have 2 x-intercepts. We have 1/2, 0. And we have negative 2, 0. So we know this parabola, because it's a quadratic, quadratics are parabolas, we know that parabola, the graph of it, crosses the x-axis at those 2 locations. Now for the y-intercept, put it over here, they're usually the easiest ones. We're going to leave y alone, but then every x term is going to be a 0. So you see, anything with an x goes away, and all that you're left with is negative 2. So my y-intercept is 0, comma, negative 2. Most of the time when you want to start your graph, they're the things that you're going to want to calculate first, because they're the simplest ones to calculate. So if you're using a table, you may not actually put any of those values in there, but also if you have x equals 0, you are finding the y-intercept. And then what you could do is with this y equals 1/2 x squared minus 4 is find the x-intercepts, and then you'll have even more points. All right, x-intercepts. One way to figure out what a graph's going to look like. Another way, we'll call this 3, is to look at symmetry. Okay, symmetry. All right, there's 3 types of symmetry that we could look at. One type is called y-axis symmetry. Okay. So I'll just do a little simple graph over here. Y-axis symmetry means that if you were to have, let's say, something that looks like this, okay? If you were to flip that over to the other side of the y-axis, it has the exact same shape. I mean, as best as I could draw that, okay? So think about this. If you could just picture that was a piece of wire and like it could rotate about its center. If you were to flip that thing around the y-axis, if you're able to do that, then you have y-axis symmetry. So what that means, like numerically with our coordinates, is that if you have a coordinate xy, then negative xy exists. Right? So that means, let's just say if x was 2, if you had whatever the y coordinate is at 2 and whatever the y coordinate is at negative 2, they're going to be the same. So that's y-axis symmetry. You could probably imagine what x-axis symmetry looks like. So I'm going to do this sort of the same thing. If I had this same shape, but I could spin it around the x-axis, that's x-axis symmetry. So if you had a coordinate xy, then You also have another coordinate at that same x coordinate, but it's negative y. Okay? And then the last type is origin. Origin symmetry. That one's a little bit more difficult to draw, but I'm going to do my best. Let's say you had that coming from the origin, and you had the same thing going in the third quadrant. So coordinate-wise, if you have xy, then negative x, negative y has to exist. All right, so we could test equations for this type of symmetry. Let me give you an example. Let's say we had y equals 1 over x squared plus 5. Now that, probably you can't imagine what that would look like, right? But you might be able to at least know what the symmetry of this equation would look like. So here's what you do. So for x-axis, you replace y with negative y and see if equation remains the same. Okay? So let's try that. So we're going to do x-axis over here. All we're going to do is, instead of having that y on the left-hand side, we're going to plug in a negative y. We don't change anything else. And then what I'll do is I'll solve for y, which means I'm going to put that negative sign on the other side. And we have negative 1 over x squared plus 5. So is the thing that I'm boxing the same as our original equation? It's not, right? So we do not have, so no x-axis symmetry. All right? The only way a symmetry is going to be true, or if you have it, is if it matches the original equation. So for y-axis symmetry, you replace x with a negative x to see if the equation's the same. I won't write that all out. Okay? So let's try here our function here. So for y-axis, so we're leaving the y alone, but now we're plugging in negative x. So here's what you have to do here. X is being squared, so now we have to square negative x. And then, again, just simplify the equation. So y equals 1 over x squared plus 5. Ah, is that the same as our original equation? Yeah. So this means we do have y-axis symmetry. We have it. And then finally for origin, you replace x with negative x and y with negative y, and then see if it's the same. So we'll do origin. So we're going to have negative y equals 1 over negative x squared plus 5. So we have y equals negative 1 over x squared plus 5. So is that the same? It's not, so no origin symmetry. Okay. So that's our way of testing whether functions have different types of symmetry. Let's see, what do we got? 9:30. So let's do this. Just we'll do one more example. So here's another equation, 4x, y equals 4x minus x cubed. So we know what we have to do for each of these. For x-axis, we're plugging in a negative y. So negative y equals 4x minus x cubed. So that means y equals x cubed minus 4x. That's not the same as our original, so no. We do not have x-axis. Let's try y-axis. So now we're going to plug in negative x values and simplify. We get negative 4x, and this is negative x cubed is negative x, but we're subtracting it, so it's plus x cubed. That is also not the same, so we do not have y-axis. And finally, origin will have negative y equals 4 times negative x minus a minus x cubed. So negative y equals negative 4x plus x cubed. But then when I move that negative sign over, I get 4x minus x cubed. And look at that. That's the same as the original. So yes, we do have origin symmetry. Yes, sir.
Can you assume if you do like the x-axis and the y-axis and the both no, can you assume that origin is yes?
No, because there's some that have no symmetry at all. Okay. So, folks, that's it. I mean, this section, like I said, some of these chapter 2 sections are small. So what I'm going to do for section 1.2 homework, this is on page 195. What are we going to do here? We're going to do 25, 27. They're going to be plotting using a table of values. And then, we're also going to go to, it's pages 195 and 196. So 25, 27. And then finding y-intercepts and x-intercepts. These will be problems 51. And then 57 to 61. And then testing for symmetry is going to be 65 to 69. And again, these are all odd. So let me make this clear. For the homework you're going to submit for Tuesday, right? It's both sections, 1.1 and 1.2. But because it's 2 sections, I'm going to make it a +4. Instead of a +2. Does that make sense? But they'll just be one Dropbox, right? Just make one big document, put it all in the one Dropbox, and it'll be a +4 instead of a +2 because it's 2 sections, okay? One other announcement I have for next Tuesday is I will not be here next Tuesday. So don't come to class Tuesday. But what I'm going to do is post a video on section 2.3. All right, it won't be a long video because there's not a lot of questions interaction because I'm just talking to the screen. So all I'll do on that Tuesday is assign. I'll complete I'll complete 2.3 in the video and assign a homework. That homework won't be collected, but on next Thursday we'll have a quiz on the sections we covered today, 2.1 and 2.2. Everyone got that? So quiz next Thursday on 2.1 and 2.2. No class on Tuesday, but there will be a video posted on section 2.3 with a homework assignment that will not be due in a Dropbox next Thursday. Everyone good? All right. That's it. We will be done a little early today. Excellent. If you wanted to take pictures of the homework, you just come on up and go ahead and do that. There's 2.2, and you could just page back to 2.1, whatever you need. You too.